We're going to talk about inverse functions, and then we're going to talk about like function notation, because the second question we have really is more of a focus on this than it is on inverse functions. But let's start with this. So here's function notation. The function with the variable x is equal to 3x plus 2. Do you know what type of function this is, or what type of graph this is? If you looked at it.
Well, this is a function.
If I were to graph it, do you think this is a curve, a squiggly curve, a line? What do you think this might be? And sometimes it's hard to see this way. I'm gonna do something else. I'm gonna write it not in function notation, just so it's a little clearer to us. When you see it, ooh, that is a funny too. When you see it like that, does that ring a bell to what type of graph this might make?
Well, I know the slope is 3 over 1.
So if we're talking slope, that already means we're talking about a linear function. Okay, have you guys used that word before? Sometimes, yeah. Okay, straight lines, and that's what this is. This is a straight line because we have an mx plus b. Straight lines are called linear functions. So instead of using y, we've used f at x. Well, that's fine. There really isn't a giant jump from that, okay? But our second question is going to be a bit of a jump. It's going to do something a little different. And think of it to start as we've just replaced y with f at x, saying that there's a function with a variable x in it. So when we write the notation f at -1 to the x, we're going to look for the inverse of the function.
So the opposite.
Yes.
Not, well, sort of.
So the question is, how do I do that? Now, the inverse of a function, okay, let's say, ooh, this is tough for me. I'm going to do it like this.
Switching x for y?
Yes. So if this is the original function, what ends up happening is there's a 45-degree line. Think of it going through the graph like this on a positive slope. So what ends up happening is the new function we're going to find is the inverse on that blue line. Okay, think of it like it's flipping or folding. Okay, that's my best, that's not really a great one, but that's like a sketch of what the inverse could be. Okay, so in order to find the inverse of the function, what we can do is replace f at x with y like we had done over here, right? I'm going to say y is equal to 3x plus 2. And think of that as, that's the original f at x, okay? And then for the inverse, we're just going to swap x and y. So now I have x is equal to 3 plus 2. But we don't really write functions equal to x. We write them y is equal to something, just because it becomes a little simpler for us to graph the way we've written our Cartesian plane, okay? So I'm going to go back through a bit of isolating. So I'm going to take this 2, bring it to the other side. I get x minus 2 is equal to 3y. And then I'm going to divide all the terms by 3. This one essentially becomes a 1, okay? So we get y is equal to x minus 2. And it's not too common that we write y on the right side of the equation, so I'm just going to rewrite it again over here. Y equals
Wouldn't
x
it be x minus 2 over 3?
Oh, yeah, sorry. You're right. There should be over 3 and over 3. Both of those are over 3. I missed that on this part. Thank you. So, if we have something like this here, whereas like in the variable is part of a fraction, we actually tend to replace that. We don't tend to write the variable as the numerator of a fraction. We'll write it as this: 1 over 3 times x minus 2 over 3x. And the reason we do that is so, with at least linear functions, that 1 over 3 represents the slope that we're used to seeing, okay? And then the constant value is -2 over 3. So we can actually graph to make sure that these are inverse functions. So I'm going to take us to that graphing page. What was the original? 3x plus 2. So let's say y is equal to 3x plus 2. Didn't write y in. There we go. So we have this. I'm going to now try to graph the second one. We said y was equal to 1 divided by 3 x minus 2 over 3. Is that what we said?
Yeah.
I believe so. Okay. And the last thing I'm going to do,
Just put the line in the
yes.
middle.
Do you know what that line, how I could write that?
Reflect. Oh, sorry. I thought you meant the name. Y is equal to, I don't remember.
X.
Oh.
Y is equal to X. So I've now got a dotted line there. And does that kind of look like a reflection if we were to fold the page? I know it's difficult to mentally do, but if we were to fold that page, the red line would become the blue. If we folded it along the dotted line, and vice versa, if we folded the other way upwards, the blue line would fold over the red. So that's the inverse of that linear function, okay? So we've now built it, but in function notation, how do I write this? I'm not going to write it f at x is equal to this because that's not f at x. Oh, it's a funny arrow. I don't know why I drew it there. I'm not going to say that f at x is equal to this because this is what f at x is equal to. The reason we use this f at x is because we can have tons of different linear equations on a page. I could have a function called g at x that represents a different one. Maybe it's like, 2x minus 1. I could have h at x equal to 3x. I could have a at x is equal to negative 4 over, those are bad examples, 3x plus 2. I'm just making up different linear equations. What I'm saying is this letter here denotes different functions, okay? So, instead of calling the inverse g at x, h at x, a at x, any other letter of the English alphabet, we say that there's a relationship between f at x and the inverse. So we write it as f to the negative 1, power of negative 1, at x is equal to, and then we write this new one, 1 over 3x minus 2 over 3. And the original f at x is equal to 3x plus 2. So if you notice, we're still using that letter f from the alphabet, and we use f in the standard equation because it's a function. It's the first letter of that word. We're using f to represent both of these because there is a relationship. We know that one is the inverse of the other. Okay? So, now that we got how to do an inverse, here's a much tougher question. Okay? And I got to remember these two values. I'm going to write them out on the next page here. I'm going to write them in different colors so we remember. 3x, my memory's terrible, plus 2. And the inverse of the function is equal to 1 over 3x minus 2 over 3. Okay, so here's the tough part of the question. This function notation. The question is asking, is this true? Does the left side equal the right side? Well, how on earth do I write this here? Okay, I want you to...
Don't you have to put this into there?
Amazing. That's exactly what I have to do. What this is saying is take the inverse function, which is this one here, and replace this part with this part here, and plug all of that in to where the x is in this function here. So let's try that step by step one more time. So I would say f at f negative 1 to the x is equal to, okay, so I take f at x, this is the original function. So I'm going to say, and I'm going to color these a little different. Here's an f negative 1 x, okay? The original function is 3, and instead of writing the x, we're going to replace it plus 2. So if you notice, I've brought down the 3, I've brought down the 2, but instead of x, we are going to put this whole part of the function.
3x minus 2 over 3.
Exactly. And now I simplify this equation, okay? So that was the green part. So instead of continuously writing the left side, I'm just going to continue to simplify the right. So this 3 gets put into here. And when we distribute the 3, I'm going to show you a real quick trick. This 3 just multiplies by the numerator. That becomes 3 over 3, which is just 1. So that's x. And this becomes 3 over 3. So this just becomes negative 2. And then we have plus 2. Okay? And these two things, they're going to disappear. So it's just equal to x. That's what the left side is equal to. We've just figured that out.
Wait, how is that one equal to
Sure.
2?
So let's zoom in on this one here. If I distribute to 3, I get negative 2 over 3 times 3. Okay, and remember when we multiply fractions, it's the top by the top over the over the bottom by the bottom?
Wouldn't it be 6 over 3?
It'd be negative 6 over 3. And what is negative 6 over 3?
Negative 2.
Hi. Thanks for calling me that. So what I did is I just simplified before I multiplied. I took these two 3's away, and it became negative 2 over 1. Thank you, honey. Does that make sense how we got to that?
Yeah.
Yeah. Okay, good. So we end up with x. So the next thing we're going to do is we're going to focus on that other function notation. So we're going to take this function here.
And do the same thing. But
Same
with
concept.
the-
Exactly. Very good. You got this. So f at negative 1. And we won't use green. We'll use, yellow is not a wonderful color here, but f at x. Actually, this part's the blue. So the original function in blue is 1 over 3, and then we're going to put something in there minus 2 over 3. And the yellow part is going to become 3x plus 2. So we took that function and put it in here. Great. So now we're going to distribute. So when we go to distribute, I'll do the rest in black from here on in. 1/3 times 3 over x. 1/3 times 3 is just the value of 1. So that's going to become just x, okay? 1/3, times positive 2 is actually going to be
2 over 3.
very good. And then we have negative 2 over 3 on this side. When I get rid of those brackets, what's going to happen to the...
They're going to cancel.
They're going to cancel out. And what do we get?
X.
So, remember that this was the right side of the equation, and this was the left side of the equation. Did they both equal each other?
Yeah.
Yeah, so we just proved by carrying this out that this side is equal to that side. Thanks.